Welcome everyone to the first exam review for OCHEM 1, hosted by the Student Success Center. So our agenda for today is going to be, we're going to try and hit on everything, and we split that up pretty much by chapters. We want to do a lecture in the breakout room where you guys are going to be doing problems, and everything's going to be 30 minutes. We're going to try focusing most on the topics that you guys put in the Google form. So the first one that we're going to do is chapters 1 and 2, structure and bonding. Yes, you will. You should. So chapters 1 and 2, structure and bonding. This stuff is, it may be a little, far back. I'm unsure. We'll get back to you on that. So we want to cover intermolecular forces, resonance, hybridization, and acid-base strength. So the first one, intermolecular forces. There are three major types of intermolecular forces that you need to know about, and from strongest to weakest, they're hydrogen bonding, dipole-dipole forces, London dispersion forces. Hydrogen bonding is when you have a hydrogen bonded to an extraordinarily electronegative element, right? And in this case, you have a delta positive hydrogen and a delta negative oxygen, and those can have an interaction like you see here. And when we see them in a big, in a macro scale, right, we see that these essentially create forces between the different atoms that make them harder to separate. And that's what leads to an increase in boiling point, an increase in melting point, things like that. The next strongest is the dipole-dipole force. Pretty much this is when you have a polar molecule. The same kind of things happens, just not quite as strong. And if you see here, this figure on, it's just a general positive and negative thing. Like if you think about units, and you can see here on the right side, we have a molecule of cis difluoroethane, and you can see on the right here, red is electronegative, blue is electropositive, and you have this kind of you have the interaction between the high electron density of one molecule and the low electron density of another molecule, the negative and the positive. The least strongest force is London dispersion forces, and these are present in every molecule, and pretty much they're a result of electrons moving around, right? So what happens is we have something like the previous slide where these electrons will localize, but it'll only be momentarily because they're moving around. So you can see that kind of in this picture on the left here. All those electrons, yes. I am. Can anyone else hear me? Okay. I'm going to keep going just because we're a little short on time today. So you can see over here how the electrons, they move to one side, and this is a momentary movement just due to the general movement of electrons. And when they localize like this, you have a momentary delta positive and delta negative, which means that you have momentary dipole-dipole forces. The problem is, since this isn't an extended effect, it doesn't continue, and it doesn't have the same strength as dipole-dipole forces. And it's good to remember that greater surface area leads to greater London dispersion forces, and that's simply because they can stack back. If there is a delta minus charge, it's easier for it to be exposed. And similarly, if we have a branched molecule, that makes it more difficult for these delta positive and delta negative to be exposed, which leads to less LDFs. So as I kind of alluded to before, greater IMFs lead to greater boiling point and greater melting point. And if you remember back to that hydrogen bonding slide, they need more energy to counteract these forces, to break those pseudo bonds between different molecules. And as far as solubility, we see that like dissolves like. So the polar-nonpolar interaction is generally weaker than polar-polar, right? Because with a polar-polar interaction, we have positive and negative charges interacting, and that's a much stronger and much more stable interaction. So polar molecules group together, which leads to, if you have oil and water, the oil is nonpolar and the water is polar. We see um, droplets of water in oil kind of ball together because their interaction with each other is stronger than the oil. Next, we're going to move on to resonance. The most important thing to remember about resonance is that a resonance structure is really, it's not what actually happens in the molecule. It's a representation of where the electrons kind of go. So the actual molecule is going to be something like the average of its resonance structures. And you can see with this carbocation here that instead of the double bond being here on one time and the double bond being on the other side on the next time, it's really a delocalization. So these can each be considered almost like 1.5 bonds, with the delta positive charge here spread out between both of these carbons. Now, the rules for resonance are they can only be valid with structures, right? You can't just, give something 10 bonds. It needs to have 4 bonds maximum for the elements we're talking about. And the other really most important thing is that only electrons move, right? We're going to be moving pi bonds and lone pairs. We're not moving atoms around. We're only moving electrons. To determine major and minor contributors, we want to maximize the number of atoms with octets, right? So if we have a carbocation, and we can give that an octet, that's even better. We want to maximize bonds instead of lone pairs generally because it'll lead to less charges. We want charge and electronegativity to agree. In other words, that's saying if you have a negative charge on an oxygen, that's more stable than having a negative charge on a carbon because oxygen is more electronegative than carbon, and vice versa. If we have a positive charge, it's more stable on a carbon than on an oxygen. And we also want to minimize charges. So that's both minimizing on a specific atom versus, so for example, if we have O minus versus O2 minus, obviously O minus is more stable, and minimizing the charge of, minimize the charge of the overall charge of the molecule, adding all the formal charges, should be constant. That really shouldn't change because you have the same number of electrons. But you do want to minimize the number of charges as well as the degree of charges. And the other thing is watch your octets. Like I said, carbon can't have 5 bonds. Don't give it 5 bonds. In general, resonance patterns can be split into 4 major things, and you don't need to exactly remember these. It's just kind of helpful to see because this is what most resonances look like. So you can have a charge next to a bond. We call that an allylic charge, right? So the example from before, you take a double bond and you can swing it to the positive charge. Or we have the opposite, where a lone pair is going to take the place of a double bond, and it's going to get kicked out over here. We have the possibility where a lone pair is adjacent to a positive charge double bond. So, for example, in this, the first one here, obviously this is going to be more stable when we swing that down, right? Because this carbon doesn't have an octet, and this oxygen is charged. But then when we swing that down, the carbon has an octet and the oxygen is uncharged. For on the bottom here, you can see that when we swing this lone pair down, and we actually get the negative charge on the oxygen, it means that this is going to be more stable. You have a polar pi bond, and this one is good to think about electronegativity with this, because if we have a pi bond where one of the atoms is more electronegative than the other, it's clearly going to be a delta minus on the oxygen, right? Simply because oxygen is more electronegative, so it's going to pull the electrons on the bond closer to itself, and that's going to lead to a polarity in this bond, which is pretty well represented by resonance, especially when you're thinking that that the resonance structure is the average of these. Clearly, if we average these out, the oxygen is going to be a little more negative than the carbon. And the fourth major resonance pattern is conjugation, which is where you have double bonds almost next to each other, and they can take each other's place pretty much. Next, we're going to move on to hybridization, orbitals, and molecular shapes. So for assigning hybridization, there are a couple major things you want to think about. The first is to check for resonance. You're always going to have hybridization found when you have the maximum number of pi bonds, because you need to keep unhybridized p orbitals in order to determine the correct hybridization. So when you find the maximum number of pi bonds, you find the number of p orbitals, unhybridized p orbitals necessary for that molecule to actually have those resonance structures, which means that the remaining orbitals are hybrid. So to do a quick example, if we take, again, that carbocation from before, and we do resonance, the most pi bonds for example, so for example, for this carbon here, the most number of pi bonds is 1, right? In this one, it doesn't have any pi bonds apparently, but in this resonance structure here, it has 1 pi bond. So that means we need one unhybridized p orbital, right? So we keep that, and then we hybridize the other 3 to get 3 sp2 orbitals and a p orbital, which means that this carbon here is an sp2 hybridized carbon. And the other important thing to remember is that the shape is dependent on the hybridization. So when we have something sp3 hybridized, that's going to generally be sigma bonding orbitals. Generally, they're going to be hybridized, yes. And that breaks down a little bit when you talk about things like hydrogen. But as far as carbons, nitrogens, oxygens, the sigma bonds are generally going to be the hybridized. The sigma bonds are going to be hybridized generally. sp, sp2, sp3. Yeah, no problem. So as far as shape, it's inherently related to hybridization, and this is something that you kind of just have to remember. sp3 are going to be tetrahedral, right? That's how we get chiral carbons, which we'll talk about later. And the bond angle is 109.5. When we have trigonal planar, that's a p orbital, right, in and out of the plane. And then the other hybridized orbitals are going to be, arrayed in a circle almost. So we have 120 degrees between each of those and 90 degrees between that plane and the p orbital. And for when we have an sp hybridized atom, in other words, for example, a carbon with a triple bond, that's going to be linear, right? And that makes sense because you only have 2 things attached. So it's just going to be linear. And the last thing we're going to talk about is relative acid and base. This was a pretty requested topic, so we're gonna go over it pretty in depth. So when we're determining relative acid strengths, we always want to compare the stability of the conjugate base, because a more stable conjugate base is gonna lead to stronger acid, right? You can imagine that as going way downhill, right? If we have a stable base down here, it's not going to want to go up to a higher stability, right? It's going to want to stay down here. So the way that I personally remember this is through, it's an acronym called ARIO, and that's pretty much to determine the stability of the conjugate base, from which we can get the stability of the acid. So the A stands for atom, and there are 2 major considerations that we have with the atom. The first is that a more electronegative element is going to be a stronger acid, and that's because when we, for example, have a hydrogen come off, right, we have more electrons than when we started with, right? Because those hydrogens, the electrons from that bond with the hydrogen go on the oxygen. So this atom is going to be more stable with more electrons, versus if we have something like carbon, that doesn't want more electrons because it's more electropositive. So more electronegative atom pretty much means that we have a higher affinity for electrons. The other thing that's important to keep in mind is that a larger atomic radius is going to be a stronger acid, and we can think about that pretty much as far as delocalizing electrons, right? We don't want electrons to be too close to each other because since they're all negatively charged, they repel each other. So in order to minimize those repelling interactions, we want them to be further from each other, right? And you can clearly see that in a bigger atom like sulfur, those electrons are going to be much farther than in a smaller atom like oxygen. So the R in REO stands for resonance. We already kind of talked about this, but electron delocalization. Yes, generally, Ahmed, radius does generally tend to trump electronegativity, yes. So similarly to how we want to spread the electrons out over a bigger atom, electron delocalization also is a really big consideration, and the best way to do that is resonance. Because essentially we're taking electrons and spreading them out over a bigger, a larger portion of atoms. So more resonance pretty much means more stable, right? If we have, for example, to use what we just did, OH versus this, we wind up with the hydrogen comes off and we wind up with the negative charge on the oxygen. On this right, we have resonance where we can make a double bond and kick this double bond up, right? So that negative charge is delocalized over both oxygens versus on the atom on the left. This oxygen has a localized negative charge. That negative charge isn't going anywhere. So this atom on the right is more stable, right? Which means that it's a stronger acid. Now, the effects of resonance and atom can be ambiguous. So I would ask your professor which they want you to look at more. And this, you don't need to think about this too much, but this carboxylic acid is going to be more stable than ethyl, but something like ethanol is more acidic than propene. So it's really something you should ask your professor about, and they'll probably try and be unambiguous. The next part of REO, stands for inductive effects. And there are two types of inductive effects. We have electron withdrawing groups and electron donating groups, and they both do exactly what they sound like. Pretty much what we're trying to do here is, again, see where our electrons are. If we have an electron withdrawing group, that's going to have a similar effect as resonance, not quite as strong, but it's going to pull a negative charge away, right? It's going to, if we have a fluorine, that's electronegative, so it's going to kind of pull those electrons slightly through the bonds. And the closer it is to the atom, the more it's going to help. So we see that the electron movement is going to be towards the group, away from the charge. It's going to make our charge more positive. So if we have a negative charge, that's good, and it's going to stabilize a negative charge. And we see that with fluorines. We see that with alkyl halides. So for example, CF3. The thing to think about is that it's going to destabilize a positive charge, right? Because if we already have an absence of electrons and we have a fluorine taking more electrons away from it, it's going to kind of exacerbate that positive charge. Versus with an electron donating group, that's going to kind of push more electrons towards our charge, right? Which means it's going to destabilize a negative charge, right? It's going to make a negative charge more negative, which is more unstable. But it's going to make a positive charge a little more stable because we have an absence of electrons that we're starting to fill a little bit. And the best example we have of that are alkyl chains, especially methyl groups. And the other thing to think about is that when we have the distance that we have the inductive group from our charge is important, right? So we can have, for example, an F on this versus two Fs on this one. And the one on the left is actually going to be more stable of a conjugate base. It's going to be a stronger acid because it's that much closer to the oxygen. So you always want to determine this by whatever is closest to the charge. And I want to do an example of ranking by acidity with y'all, just because it's that's a little bit beyond the scope of what we need to know, Akshaya. It's good enough just to know that alkyl chains, methyls, and things like that are electron donating groups. Yeah, sorry I couldn't give you a better answer. Okay, so and if y'all notice that there's a lack of O, that's because you don't need to know it. So we're gonna just kind of cross that out. So let's start with atom. So the first thing to do is kind of to realize the most electronegative atom, the most protic hydrogen, the most acidic hydrogen each. And that's going to be on, if we have things like oxygens, it's almost always going to be on an oxygen, right? So those are the most acidic hydrogens in each. And in this case, all those are shown, which is nice because it helps us. The next thing to do is we're going to look at atom, right? So the first four are all oxygens, and the last one's a nitrogen. Oxygen is more electronegative than nitrogen, which means that we can automatically rule this N as the least acidic, right? As we keep going, we have all oxygens now, so that's not helping us. So next we want to look at resonance. And we can see that we have resonance in each of these three, right? So now we need to determine the degree of resonance, right? So we can see that these have resonance, this one doesn't. So, sorry, these three have resonance in the middle, and this one doesn't have resonance, right? So that means that this conjugate base is going to be less stable. This conjugate base is going to be less stable, right? So it's going to be less acidic. So we'll call that 4. And now we pretty much need to determine this difference in stability between these three. Now, if you draw the conjugate base for this one, you'll see that resonance can make our negative charge delocalized between all three oxygens. Versus in the other two structures, it's only going to be delocalized between 2 oxygens, which means this one's going to be our most stable. And then as for the other two, we have a fluorine, right, versus an absence of anything. So this inductive group here is going to actually withdraw some of that negative charge, which is going to make this more stable conjugate base, which is going to make it more acidic, right? So we can fill in the last two, right? And that's how we rank by acidity. If you get a molecule with multiple different groups, and they ask you to find the most acidic hydrogen, you're pretty much doing this within the same molecule. The different parts are kind of independent of each other. For 2 and 3, yes, I can. So if we draw the conjugate base, right, we're going to have a negative charge here and a negative charge here. So these are, as far as this goes, they're the same, right? They both have a negative charge on the oxygen and the same resonance. Yes, I will get to that in a second. So they both have a negative charge on the oxygen, right? And they both have resonance with the other oxygen. So that's not different, right? So the atom and the resonance are the same for those two. What's next is looking at the inductive effects, right? So this fluorine here is an electron withdrawing group. It takes electrons away from its surroundings towards itself, right? So that's going to kind of take this negative charge and bring it towards itself, which makes this less negative. It brings the charge closer to 0. Versus in number 3, there's no fluorine to bring those electrons away. So those electrons are going to stay more localized on the oxygen. Okay. So because we have this, this fluorine bringing electrons away, that's going to delocalize that negative charge, which is going to make it more stable. So that's how we get 2 versus 3. And as for 1, you can see if we draw the conjugate base, and I'm just going to draw the top part without the ring. So it's not the sulfur that increases the acidity of this one, it's just the fact that we have more resonance, right? If you look, we can take these negative charges, these lone pairs, and kind of bring this negative charge to each of these different oxygens. So that negative charge is delocalized between 3 oxygens. And since we have that more delocalization, right, we have a more stable conjugate base, which makes this the most acidic. More stable conjugate base means more acidic conjugate acid. Does that answer all of your questions? Are there any other questions on that? Okay, so now we're going to go into breakout rooms. So one of the other leaders just shared, one of the leaders just shared a Google Drive link to the packet that we're going to be using. We're going to work together, and leaders will be jumping from room to room to help you out if you have any questions. If you do have any questions, either raise your hand and we'll come as soon as we can, or send a message in the everyone chat with your question. So with that, we will send you all into breakout rooms, and we encourage you to use your mics.
Okay, just come back. So we will send out a key after this review of all our practice problems. So okay. I'll get started on chapter 3. Can everyone hear me all right?
Yes.
Okay, so let's start. So in chapter 3, we'll talk about basically alkanes, what cis and trans mean. We'll go over Newman projections, ring strain and cycloalkanes, and chair conformations, as well as bicyclic alkanes. So to start off, we have what are alkanes? Alkanes will be sp3 hybridized. That's provided that it's not positive or negative. We'll have a prefix before it and an ane at the end. And this is the general formula for it right here. Here's are some examples of different types of alkanes. It's one of the things that you have to memorize, especially the prefixes. So the reason why the boiling point gets a lot bigger is because the longer the chain is, the higher the boiling point is. All right, so let's go over naming. So step 1 is the main chain. So what you have to do is you have to find the longest continuous chain of carbon atoms. and use that as the base. Yeah, so if two chains are equal length, then most of the substituents is the main chain. I'll go over some examples later. So number 2, number it, the main chain, and when you do that, make sure the end that's closest to a substituent has the smallest number. So like for example, let's say you have this, right? You want to say that this is 1, 2, 3, 4, and 5, and not the other way around. And so number 3 is naming alkyl groups. So this is just for this example in here. We have this alkyl group right here, and so they're named by these prefixes. N means it's normal, so let's say like let's start like butyl, which is to this would be butyl. This would be the main chain. Iso would be like this, and it's connected to the main chain. Sec would be right here, and tert would be like this. So to differentiate what iso and sec is, sec just means secondary, which means that the atom that's connected adjacent to the main chain is a secondary atom, which means that it's connected to 2 other carbons. And for T or tert means tertiary, means it's connected to 3 other carbons. And then for halogens, these are the prefixes for halogens. This will be fluorine, this will be fluorine, bromine, and iodine. Also, don't forget when you're using alkyl groups, you just replace ane with YL. Like instead of methane, it would be a methyl. This would be a methyl group right here. And then number 4, organizing multiple groups. So this is when you have molecules like this, where you have 2 methyl groups right here. 1, 2. So this would be a dimethyl because you have 2 methyl groups. And make sure they're in alphabetical order. This is really important. So one thing that's confuses a lot of people is that over here, only the iso is counted towards the alphabetical part. So when you have a N or a sec or a T, you look at the base alkyl name. So if it was a sec butyl, you would look at the B. Same with T butyl. However, if it's an isobutyl, you would look at the I. So iso would be the only exception to the alphabetical order. And then, so for complex, it's basically it's basically another main chain. You do it all over again, except that you have to put parentheses around it. And this is itself, it's as if like you're naming another main chain within a main chain. That makes sense. So for here, I'll do a quick example. we count the longest chain, which is this 1, 2, 3, 4, 5, 6, 7, 8. So octane, and then number it. So we have 1, 2, 3, 4, 5, 6, 7, 8. If you do it the other way, it would be 1, 2, 3, 4, 5. However, we want it to be in the least number, so we keep it at 4. And here we have 1, 2, 3. So this would be a propyl. And with this kind of orientation, this this carbon is a secondary. Oh, actually, yeah. So with propyl, it's only either N propyl or a isopropyl. So this would be a 4 isopropyl octane. All right. And so I'll do one more example here. So let's do the second one. So we have a butane. So we would draw the base first. So 1, 2, 3, 4. You have 2 bromos, so this will be the second one. So this would be Br. And we have 3 ethyls. So ethyl is it's an ethane alkyl group. So that's 2 right here. But actually, let's change this to methyl. Because if it was ethyl, this would be the longest chain. So yeah. Okay, so I'll go over to the next part. Do you guys have any other questions? Is to put in a text chat. Alright, for now we're gonna go over cis and trans. So for cis, they point towards the same face. Trans is opposite. Just remember that they cannot interconvert without breaking and reforming bonds. So this would be cis, this would be trans. Okay. And so let's go over Newman projections. I know this is one of the requested ones. So when you look at a molecule, either pick one of the left or right side to look at it. So in this case, this will be viewed from the left. So what this vertical line means right here, that means that it's the solid line. So these are vertical lines, right? This will be the solid lines. What on the right hand side, if it's on the right side, they will be a wedge right here. And if it's on the left side right here, they will be a dash. That's if you're looking at it from the left side. It would be reversed if you're doing it from the right. But in this lecture, we'll be looking at things from the left. So the next one is eclipse versus staggered. So eclipse just means that they're basically on top of each other. So they're like overlaying each other. So that's the angle would be 0 degrees. The complete opposite of that will be staggered, which means that they are separated as much as possible, which in this case is a maximum of 60 degrees, or a minimum of 60 degrees on both sides. And then skew just means any angle in between 0 and 60. And then what you need to know is that this uses a lot of energy, whereas this has the least energy. Gotch. Yeah, gotch. It just means that when two atoms are gotch, means that they are adjacent. They're 60 degrees from each other. So like these are gotch, and then there's also anti. Anti just means that they are 180 degrees away from each other. So this would be, what would you call it? This would be anti. And I forgot what the other name was. The other name would be like there. I think, yeah, I think that's all the names, I think. All right, so now we'll go over stabilities. Um, so with bond angles, yes, they're applicable to staggered conformation. So what cycloalkanes? So alkanes are usually sp3, right? So that means that they have a bond angle of an optimum bond angle of 109.5 degree bond angles. So if it gets less or more than that, there we get ring strain. So with this isopropane group, it reduces to 60 degrees, which has a lot of ring strain. And as we move up, if we increase the number of carbons, the strain gets decreased until we get to cyclohexanes, which gives each bond angle exactly 109.5 degrees. So if you're looking at all these, cyclohexanes probably is the most stable because of its bond angles. And then so for cyclohexanes, we have three conformations. We have chair boat and twist boat. So here, this is a chair right here. This is a chair. So with chair, we have an end going up and end going down. With boat, let's see if I have it here. Yeah, with boat, you have two ends going up like a boat. Let's see, boat. And twist is basically in between, right here. Let's see. Yeah, so the difference between the chair and a boat is that chair is always staggered, whereas boat, they are eclipsed. So if you're looking at the most stable, chair would be the most stable. And we have axial equatorial positions. Axial means that the bond or the substituent is pointing in the axial direction. So over here. Yes, boat is the least stable. And then the equatorial position just means that the substituent is pointing in the, I guess, the equator of the molecule. So if you're looking at it from the side, it's around the molecule, whereas the axial is just on top and bottom. See over here. And this is where we get, this is what happens when we have that chair conformation. And the last part is we're going to talk about conformations of substituted cyclohexanes. So chairs, they can be flipped. They can go from Okay, it goes really bad. From here to right here. And when you flip them, the all the axial positions turn into equatorial, and all the equatorial turn into axial positions. And so a special thing about T-butyl and other bulky substituents, they will prefer the equatorial position, most because um, this equatorial is away from the compound, and that will reduce the steric strain. Because if it was in the top, you have uh, you have atoms of like hydrogen right here that will get in the way of the bulky substituent. So that's why it always wants to be equatorial. Yeah, so what happens is it momentarily becomes a boat, and then it switches off to the other shared conformation. Yeah, so over here it's called diaxial interactions. This is less stable because of, like I said, of these hydrogen interfering with this whole molecule. So this is more stable because of that. Same with this. If you have two bulky groups, they will have this. They will repel each other, and that will be very unfavorable. Whereas here they're away from each other. Mm, yeah. So when you're looking at, if both of them are trans, such as this, the longest chain or the most bulky chain will prefer to be in the equatorial position. So for torsional strain, that's more so on ring strain, I would say. But I mean, yeah, I guess steric can just also has some to do with torsional strain as well. Basically, if any kind of strain is a steric hindrance, if you think about it. So anything that makes this not equal to 109.5, if it's an sp3, that will cause it strain. And with strain, you will have some kind of sterics involved. Okay, so now that's all I have for chapter 3. We'll go into our breakout rooms. So I'll go over the answers after a couple minutes. I'll let you guys look over the questions. All right, I'll start working on the first problem. Let's see. Okay. So the first one we got with this. This will be a 2,3 dimethyl pentane. Next one would be if you guys have any questions, just text it in the chat. This is weird. Let me restart this. Alright, hopefully that fixes it. No, this is mm, oh yeah, sorry. For ISO is when, so let's, if we're talking about the butyl chain, so if N, yep, different types. The N butyl, that's just the normal one, so it'd be 1, 2, 3, 4. This is the main chain, so 1, 2, 3, 4. We have ISO, so I just know. You have like this. So ISO, I think of it like ISO as in like isolated. So this group right here is away from this chain, the main chain, whereas the sec butyl, it's the one that's closest to the chain right here. You know what you think of sec is that this is a secondary It's carbon secondary. And then we got T-butyl, which is right here. This is a tertiary. So when you see iso, think of it as like a fork on the end. So like isopropyl. Isopropyl. It's like this. You have that. You have like I guess a Y at the end, just like isobutyl. That goes for any alkyl groups. So we can move on to number 2. Okay. Hold on. What this is. This works. So we're going to be looking at it over here, looking at it from this side. So, so like I said in the lectures, solid lines are the vertical. Wedge will be on the right, and dash on the left. So we have our here. Okay. So let's start with this one right here. This will be in the front. So the front is always the one with the 3 lines intersecting. So okay, so our wedge is the NH2, so that will be on the right side. H2. Our dash we don't see it, but it's the hydrogen right here. And then the rest is the solid line is in a vertical. So that would be a CH2, CH3 here. In the second portion right here, the back carbon is always the circle one over here. So our wedge is the F. So this is CH2, CH3. Our solid line is this methyl group, CH3. And then lastly, our wedge, which is the H, is the H right here. And then the next one, we have drawing it again. So from this side, we have the wedge with fluorine. Our dash is hydrogen. The straight line is methyl. And for the back carbon, our wedge is the OCH3. And then another methyl for the vertical, and then the dash is the H. Okay, so now this one. Okay. So first we look at the the vertical substituents in this Newman projection, which is this propyl group and this ethyl group right here. So that's 1, 2, 3, 4, 5, 6, 7. So that's 1, 2, 3, 4, 5, 6, 7. And this is the front carbon is the 1, 2, 3, the fourth one. So it will be this one and this one. Right, so our methyl group on the front is a wedge. In the back is the hydrogen. And the next carbon, the wedge is the hydrogen, and the back is the bromine. Yeah. Next one. Okay. So we look at the vertical line. 1, 2, 3, 4, and 5. So 1, 2, 3, 4, 5. And we're looking at the the third one, and the fourth one. No, actually, no. It's the second one and the third one. Okay, so our OH is on the right side, so it's a wedge. And dash is the H. Wedge here is the H, and the dash is the chlorine. So that's for number 2. So number 3, rank the following conformations in order of increasing potential energy. Like we said, so eclipse, staggered, and the skew right here in the middle. So this is lots of energy, and this is least energy, and from highest to lowest. So for question number 3, we look at the staggered ones. So here the staggered ones are the first one and the second one, and the last one. So this is the first one and the last one. Since they're both staggered, they're going to be the least energy. And the only difference is the placement of this bromine. So when they're both eclipsed, or when they're both staggered, you have another set of categorization, which is anti and gauche. Anti will have the least energy, and this will be most. So here we have these two bromine and these two bromine. Since these two bromine are the first one, these two bromines are adjacent to each other. So that will make this gauche, and this, since they're direct opposite of each other, this is anti. So this would be number 1. The last one is number 1. The first one is number 2. And the next one, we have the second one, we have a eclipsed. Both these are eclipsed. The fifth carbon. What are you talking about? Are you talking about this one? Oh, okay, so if we number the vertical lines of the Newman projection right here, we have 1. The intersection between all 3 lines is 2. The big circle is 3. The next one is in the bottom, which is 4, and this is 5. Makes sense? Yes, this is correct. Because we have 1, 2, 3, 4, and 5 right here. Does that make sense? Yes. Okay, let's move on. So the second and the third one are both eclipsed. The only difference is the bromine here are on top of each other, and here they are like at least separated. So bromine, they're really big atoms, or really big elements. And if they're on top of each other, there's a lot of steric hindrance in here. Whereas this one, they have this much space of freedom. So if the one with sterics will have the most energy, most potential energy. So this would be a 3. This would be a 4. Alright, so moving on to number 4. We got ethyl cyclohexane. So we have an ethyl group on a cyclohexane. So I'll draw my chair. So if it's an ethyl group, we want substituents to be on the equatorial position. So over here, we would put it going downwards, versus if it was over here, this is axial. So this would be the correct one right here. One moment. Give me 1 moment. Okay. Nice. What's the next one? Next one will be this. I'll draw the chair first. Alright, so this dimethyl right here, it will be, since there's two substituents, one will be axial, one will be equatorial. Since they're identical, it doesn't really matter. However, this one, this is the next, this isopropyl group, this is more bulky, so it will be in equatorial position, so it'll point downwards on this side. The next one we have this. Again, this is more bulky than this. This propyl group is more bulky than this ethyl group, so that's why this is equatorial and this is axial. And it's because they're cis, they have to point towards the same direction, so they're pointing both upwards. The last one, it's a bit tricky. since they're both bulky groups, both of them, one of the other, and they're trans, both of them are what have to be different. And since one of them cannot be in the equatorial position, it has to be a twist. And you only use twist when both substituents are bulky and cannot be put in the axial position. So something like this. Yeah. And the last one, some A, you see that both of them are pointing downwards, so that'll be a cis 1,3-dimethyl cyclohexane. B is also a cis since they're both pointing downwards, and this time it's 1 and 4. And part C is trans because one is pointing up and one is pointing down. And that should be it for this. Alright, so it's now 12. I will bring us all back in the main room.
All right, so the last part of our review today is going to be on your most recent chapter, chapter 5, which is stereochemistry. So first we want to talk a little bit about RNS nomenclature, how we decide which is which. We're going to talk about isomers and essentially deciding the relationship between two molecules. We're going to talk about mesocompounds as well as Fischer projections. So to begin, RNS nomenclature goes by something called the Kahn-Ingold pre-log convention, which is essentially how we rank our substituents, right? So atoms with higher atomic numbers receive higher priorities. If your screen is zoomed in, you can go to that little magnifying glass on the left side of the screen and change the size of it. So atoms with higher atomic numbers receive higher priorities, right? We have, for example, if we're looking at alanine, the molecule on the right, this nitrogen is going to be ranked highest priority because it has the highest atomic mass compared to the carbon, hydrogen, right? So that's going to be a highest priority group. And then when we have ties, we always use the next atom along the chain. So for example, numbers 2 and 3 are both carbons, right? But then when we continue along the chain, we have an oxygen on one versus hydrogens on the other. So that's going to mean that number 2 is higher priority than number 3. And then we treat double and triple bonds as essentially double counting or triple counting the element. So this carbon, number 2, we would essentially count as being bonded to 3 different oxygens. So when we have the lowest priority group pointing backwards, right? Like this hydrogen here is on a dash. We consider that being, when that hydrogen is on a dash and these other groups are clockwise, we consider that R, but in this case, we have 1, 2, 3 in this order. So that's going to actually be counterclockwise, which is S. So this is going to be S, this chiral center. If we have the opposite and the lowest priority group is facing the front, then we need to flip those. And you can think about that as in we're pretty much just turning the molecule around. And if we turned it around, something that looks clockwise will actually be going counterclockwise, and vice versa. So here are just some good images, and if you look, we really have to kind of rotate the molecule in 3D in our heads to get the proper stereochemistry, right? So for example, this bottom one here, we want to rotate it around 120 degrees, like this, like the arrow shows, in order to get that lowest priority group in the back. And then we can clearly see that we have the counterclockwise. And same thing with that top one there. And here just shows well pretty much how we count double and triple bonds. This is connected to 3 carbons. So continuing, we're going to talk a little bit about how we determine the relation between molecules. Structural isomers, you guys all know what these are. They have the same formula, but are connected completely differently, right? So for example, these both have the formula C6H14. They look completely different, right? They're connected in a completely different order. And same with down here. Now, stereoisomers and conformations are essentially the same formula, but there is something slightly different about them. And when we're talking about chirality, then we have essentially the order of the bonds is different, and we can have enantiomers, in which every single chiral center is going to be switched around. So if we had R, we had S, and if we had S, we now have R. Versus we can have diastereomers, which are going to have at least one, but not every chiral center opposite. And obviously we can only have that when we have 2 or more chiral centers. The other kind of relationship we can have is with conformations, which are really when it's the same molecule, but different ways of looking at the same molecule. And the best way to look at that is, for example, in a Newman projection, where we kind of just rotate one side without looking at the other. With double bonds and rings, we have cis and trans isomers, right? We can't just rotate those and have it be the same thing. So they are isomers, and these are actually also referred to as diastereomers. And that's, again, like trans versus cis. And here's a good flowchart that kind of helps us to see this. And I went through all this, so I'm not going to talk about it, but that is, when we send out the slides, this will be good to help you. And again, you can see here, especially in the ring, how we can't just rotate this molecule to get from cis to trans. So now we're going to talk a little bit about mesocompounds. And that's a special kind of molecule that has chiral centers, and it has an internal plane of symmetry, which means that the 2 enantiomers are actually kind of the same. So if you look at this example here, and actually there's a picture from a Khan Academy video with model kits that show this. We take this molecule, right? It's going to be cis dichlorocyclopropane, and we flip all the chiral centers, right? We make this R an S, and we make this S an R, and we get this molecule here, right? So we would think that's the enantiomer. But really, if we take this molecule and we rotate it 180 degrees, right? So we look at it from the other side, then we see that it's actually the same as the original molecule. And we can see that this internal plane of symmetry is the reason for that. So when we have an internal plane of symmetry with more than 2 chiral centers, we're actually going to wind up having what's called an enantiomer, which is, we're going to have what's called a mesocompound, which is when the enantiomer is really the same thing. And the important thing to think about with that is that we have one less overall stereoisomer than we would otherwise, right? Instead of 2 to the n stereoisomers, where n is the number of chiral centers, we have 2 to the n minus 1. And the last thing we're going to talk about are Fisher projections. which are really good way, especially with biological molecules, of showing stereochemistry. So if you look at this thing here, we have essentially, we're folding the backbone. So everything's pointing back, which means that our substituents are pointing towards us, right? So all these vertical lines are wedges versus all the horizontal lines are, sorry, all the vertical lines are dashes, whereas all the horizontal lines are wedges. And this is good because it helps us to easily see stereochemistry, right? So if this 4, and we can look at it from up here. If this 4 is our lowest priority group, then clearly we can see that we go like this, which tells us quickly that it's going to be R. So when we have something with multiple stereocenters, that helps us to easily see it. And like I was saying here, if you can see clearly in an image like this, that those are mirror images. So you can quickly tell that those are enantiomers. Whereas if we have something like, yes, I see hand raised. Is there a question? Okay. All right. So if we have something with more than one chiral center, right? For example, this and this, and we'll call this. If on the other one, we see that one of these, I said that it would be R, but since the H is always be S. On which one? On the previous slide? Oh yes, I apologize, it would be S. You're right. Yes. Oh, okay, I just erased it. Basically, we have something like this, right? And I'm gonna just call these A and B to show they're different. It doesn't really matter what they are as long as they're different. If we have that, and then we have this, where only one is different, we can clearly tell that those are diastereomers because we obviously haven't changed every chiral center, but only one. And that's the value of Fisher projections. Now, when we're looking at RNS configurations of Fisher projections, when we have the vertical line, the lowest priority group is going to be the lowest priority group is going to be coming towards you, right? So it's, for example, over here, this H is coming towards you, and then we circle the others left. So it looks like it's S, but it's actually going to be R, right? Right. I know we kind of rushed through that. So are there any questions? Or is there anything I'll go more into? You can either type it in the chat or raise your hand. Meso compounds? Yeah, so meso compounds are, the main thing to remember is that they have an internal plane of symmetry, right? So, okay, we'll go back to RNS in a second. Okay, so compounds are essentially when we take the enantiomer, but the enantiomer happens to be the same as the original molecule. And that only happens when we have an internal plane of symmetry. And the importance of that is that rather than something having 2 to the n stereoisomers. Since the enantiomer of this molecule is the same as its original one, it's actually going to one less, because we would be double counting this molecule if we call these separate stereoisomers. And that's why we talk about musical compounds as something special. For determining R and S, what specifically about determining R and S? Anything, or just kind of how to do it in general? Okay. So in general, right, it's really all it boils down to is when we put that lowest priority group in the back, whether it goes counterclockwise or clockwise, right? So you can see this here. This is going to be counterclockwise, which makes it S, and this top one is going to be clockwise, which makes it R. The problem with that is trying to see what's in the back, right? So after you see where in the back it is, then that's what you need to kind of see about it. So it's always, when you have this lowest priority group in the back, going clockwise is R and going counterclockwise is S. So you always want to look specifically with this in the back. And that's not a great explanation, but with 2D, it's really difficult to kind of show you that. All right, Fisher objects I see. So determining what type of isomer they are in Fisher projections is really, it's really nice. It's unusual looking at them. We're basically we know that we have it's an enantiomer if we switch every carbonyl set, right? So let me draw it like that. Actually, one of the other moderators wants to say something about RNS, so I'm gonna let him take the wheel.
Right, yes, sir, what were you going over with? Alright, so I just want to point out something. I guess it's like a trick to remember what R and S is. Let me go back to that. Is it here? Okay. So it's right here. So we have this R that's going this way and S going this way. I tricked that if you don't know which was counterclockwise and which is clockwise, this is a trick that I use. So when you write an R, when you write on R, you draw it this way, right? That's clockwise. When you write an S, like this, you're going this way. So that's counterclockwise. So this only applies when the lowest priority group is in the back. So this is just a special trick that you can use to, if you don't know if counterclockwise is ROS and vice versa. Yeah, that's all I wanted to share. That's it. Right. Okay, back.
All right, so real quickly, I'll finish up on Fisher projections, and then we'll move back into our final breakouts room. So the good thing about Fisher projections is that you can pretty much tell whether something is an enantiomer just by the side stuff is on, right? So for example, if we're looking at what we know is the mirror image of this, right? Where we switch every side of everything, right? So this OH goes from the right side to the left. This Cl goes from the left side to the right. Because we're switching everything, that has to be the enantiomer. Whereas if we only switch, for example, one of these, I'll draw down here. So let's say we keep the OH in the same place as the original one, and we switch the Cl, so it's on the right instead of the left. We kept the OH the same, but we switched the Cl, which means that one chiral center is different, right? One chiral center is different, which means that we have a diastereomer rather than an enantiomer. Yeah, that's really the importance of Fisher projections. So with that being said, are there any other questions? It can be on chapter 5 or any of the other chapters, just before we go into our final breakout session. Yes. You can use RNS to determine which type of isomer it is, and it's actually the only foolproof way of doing so. So if you want to, we recommend going back if you have time and checking all those enantiomers and diastereomers, specifically by assigning everything RNS, but only if you have time. With meso compounds, you always have one less stereoisomer. So rather than having 2 to the n stereoisomers, right? So in general, it's 2 to the n. In general, it's 2 to the n. With meso, it's 2 to the n minus 1, because we don't want to double count the meso. Yes, and we'll be sending these out after the slides. And if you just search isomer flowchart on Google, this will come up, something like this. Yeah, no problem. Anything else? All right, then we'll send y'all back into your breakout rooms.
All right. I'm about to start going over number 1. Okay. Yes, you will be able to. We're also going to post this on our YouTube channel as well, so you can access it there as well. Alright, so I'll start going over 1A. So here, hold on. So the question asks it to describe the relationship. So here, since we have charges, positive charges moving around, and there aren't any chiral carbons, we don't see any wedges or dashes in here. This would be resonance, yeah. Yes, resonance. Because this positive charge is circulating around this portion of the molecule. Next one is okay. So here, since they're all sigma bonds, there won't be any resonance involved in this molecule. And then, so now we have to find the difference between these two. So if we were to draw the chair conformation on the first one, it would be, let's try it out. So I'm going to call this 1, 2, 3, and 4. 2, 3, and 4. So number 1 is pointing towards you, so it should be pointing up. Number 2 is pointing towards you, so it's pointing up as well. Same with number 4. So the only difference is between these two. And because of that, these will be, the relationship would be, yes, they're rumors. Okay. Next one. So the only difference is one, actually, okay. So the only difference here is the the perspective of this molecule. So let's check if it's the same molecule or not. We can start by designating R and S configurations for these compounds, or these chiral centers. So over here, on the left, this will be number 1, this will be number 2, this will be number 3 and 4. And so this will be an R because it's clockwise. And from over here we have 1, 2, 3, and 4. And since the lowest priority group is in the front, this will be an R as well. And so I'll do this again. 1, 2, 3, and 4. This will be an R because the lowest priority group is in the front. 1, 2, 3, and 4. And R as well. So these are, since they both are, that means that they both have the same configuration. So these are the same compound. Okay. Next is, but if you guys have any questions, just put it in the chat. Just type it in the chat. Okay, so the only difference is the placement of these double bonds right here. Alright, so if we put a mirror image right here, it's basically flipped. However, actually no, wait, no. If it was flipped, if it was a mirror image, this would be a dash as well. But it's not a dash. So these two are two different compounds. And if their only difference is the chirality, then these will be, oops, this would be in enantiomers. Oops. There you go. Next one. So with this, there's two ways of doing this problem. One is actually drawing out the bond angle representation of this, and the other one is visually flipping this molecule around. So here, the back carbon has a fluorine and a chlorine, whereas the front carbon has a chlorine and a fluorine as well. And basically, what it is just these two molecules are viewed from the opposite direction. Okay, so if we were to draw it out, this is what it would look like. So we have, so if you're looking at the vertical lines, we have 1, 2, 3, and 4. So 1, 2, 3, and 4. 1, 2, 3, 4. This will be the front. This is the front. This is the back. T-beetle over there. So that'll be a wedge. And then we have the methyl group right here. Fluorine is a wedge. Fluorine is right here. This dash. And sitting over here, we have 1, 2, 3, 4. 1, 2, 3, 4. Here. So these two carbons are chiral. The fluorine's in the left side, so it's a wedge with a methyl group right here. And draw it up. And then okay. So they look really similar. It's just that the chiral carbons might not be the same. So this is where we draw the R and S. So over here, I'll start with this one on the right side. 1, 2, 3, and 4. Actually, I think it's easier if we look at the projection, Newman projection. So this is 1, 2, 3, and 4 right here. And if we put 4 in the very back, it would be with this. And if you're looking down, that's an S right here. And on this other molecule, we have 1, 2, 3, and 4. And looking at this way, looking over here, that's an R. So you can see how these two are different. So this will be enantiomers. You don't have to check the other chiral carbon. If one of them is different already, then they would be an enantiomer. I'll skip over to number 2. We'll give out the key later. So skip to number 2. Right, like total number of stereoisomers. So this is where we use the formula 2n minus 1. So for the first one, we have two. We have those two substituents. So it'll be 2 squared minus 1. And 3. Next one is no, actually, hold on. I think I did this wrong. We can either use this formula or we can draw it out. So for this one, you can either have wedges, one wedge, one dash, or both wedges. That's why that's why it's 3. We do that with the rest. Yeah, and this number of chiral carbons. Let me double check the slide. So I'm gonna move on to number 3 because we're running out of time. So for A, we have this. And so the trick that I like to do is all of the regular lines are in. I would put all the regular lines in the vertical position. So if you're looking at it from this way, you have CL, and this other vertical line, this other solid line is a methyl, CH3, and then wedges are on the right, so F and CH3, and then the dash is on the left, 3, and this is your wedge, H2. Yeah, actually this is a fluorine. So this is actually a fluorine. And then now we have to. The part B is drawing the same molecule but in Fisher projection. Okay, so for that, remember when we draw Fisher projections, the vertical lines are dashed, and these are wedges. The horizontal lines are wedges. So if we look over there, Let's start off with drawing the vertical layer here. Okay, since we have two chiral carbons, one right here, one right here, you would have two horizontal lines. All right, so now I would say you can pick either one to put on top or bottom, or it has to be the one that the carbon that's the most oxidized. Since these are the only carbons here. At the ends, we'll put it at the top and bottom. You have CH3, CH3. Okay, cool. So now, if we reference the Newman projection, we're basically rotating it. We have to rotate the back molecules to where this one will be a dashed, right? So rotate it this way. So we're basically twisting the molecule. So we'll end up with this. It's still the same molecule, but it's just rotated. Okay. Cool. So these are the wedges, right? So now we have these left. So you can have this one on the, oops. Yeah, you can do this on the left side and this right side. So in the front, we'll have the front top. So Cl is on the left side, so this is Cl. This is fine on that side. And then the back carbon, we have F on the opposite side, NH2 on that side. Right, for sure. Let me double check. Okay, so I'll do part C. So remember, these are wedges. These are all wedges. These are all dashed. So we have 1, 2, 3, 4, 5, 6 carbons lined up. 1, 3, 4, 6. However, this part has an OA. Oh wait, no, that's it. Okay, yeah. So these are the chiral carbons. So if you see here, these are all. So we're basically looking at this molecule from the right side. So all these molecules here are pointing towards us, while these are pointing away from us. So from there, we can have just here, OH dash OH. Oh wait, no. OH. And then this is dash OH. Then OH. So the key has it drawn from looking away from this side, but both of them are correct as long as you get all the wedges and dashes right, depending on what angle or which side you're looking from. Uh, I'll have time for like one more, so we can do like number 4. Okay, so number 4 is just they give you 3,4 dichlorohexane, right? So 6, 3, and 4 hexane or 2 chlorines, and basically there's different ways you can find these stereoisomers. One is both wedges, both dashes, or one is a wedge and one is a dash, and the other and like this, or it can be the other way around, to where this is a dash and that's a wedge. So in total we should have 4 stereoisomers. And applying what we know about RNS configurations, let's say this is a dash, right? So number of pairing groups would be 1. This would be 2 because of the chlorine. 3, and the hydrogen here is 4. And because hydrogen's in the front, this would be an R. And you do that to the rest.
Thank you, everyone. I hope this was helpful. I'm going to stop recording now.